Now we will make an announcement, okay? We proved the plants are positive and negative, the atoms positive and negative, the smallest particle they have anti. But one thing we didn't prove. Remember the verse, smaller and then an atom and bigger. We didn't see any bigger atom now. We have a big atom. If we have bigger atom, then we have new matter, a new kind of matter. We know this matter only, proton, neutron. We have bigger matter. The verse told smaller and bigger. It's in a clear book. They made the discovery of a big atom. Listen. Mango tea.
The world's largest science experiment has achieved another milestone, finding a new state of matter called a pentaquark. The existence of pentaquarks have been predicted for more than 50.
You see, this is a new atom. I told you the atom proton, it's made of 3 quarks. They found atom made of 5 quarks. This is new atom, guys. There is new matter. Maybe not 5 quarks, but the quarks may be different. There will be another, yani 20 kinds, unlimited kinds of matter there is. They didn't discover. They discovered the atom. The atom with 5 quarks. The ordinary atom that we know is made everything with 3 quarks. This new atom is made of 5 quarks. A new matter. New. They will find this now. What is it? What kind? But for example, a hydrogen made of pentaquark. What its characteristic? For example, iron made not from protons, from pentaquarks. Something totally new. This is discovered, okay? This is at CERN, at Switzerland, okay?
Yes, but they have never before been observed experimentally. The person who made the prediction, Murray Gell-Mann, changed our understanding of the structure of matter and won the 1969 Nobel Prize for Physics. Many particle physics experiments since the 1990s have claimed to have seen pentaquarks, but their claims could not have replicated or verified. The new results from the Large Hadron Collider at Geneva, yet to be peer-reviewed, are the most promising. Since it restarted earlier in 2015 after an upgrade, it has been able to produce double the collision energy, allowing scientists to observe phenomena that they have never seen before. A pentaquark, as the name suggests, is made up of 5 quarks. The environment under which this exotic particle can be found in supernova, when a star explodes and releases all.
It can, if big supernova happens, it can produce pentaquarks.
Of its energy in one moment, rather than over a lifetime of billions of years. Scientists admit that they weren't specifically looking for pentaquarks, but they reached the conclusion of its existence by excluding all of the possibilities. Now that the LHC scientists have found one type of pentaquark, they are bound to find others. When they do, the findings will help them refine their understanding of what happens in these spectacular explosions occurring frequently in the universe, all the while sitting in an armchair in an underground man-made cave in Switzerland.
We've achieved a historic first.
Okay, I hope you understand this. A new matter. This scientist, he will speak about the discovery, about the pentaquark.
There's been a big discovery at the LHC. They discovered a pentaquark. Well, actually, they discovered 2 pentaquarks. So not one, but 2. It's like buses. They've 2 coming on at once.
They discovered 2 kinds of matter, 2 kinds of pentaquarks.
This is an object of matter that's built from 5 quarks.
This is an object made of 5 quarks, and it's stable. It doesn't disintegrate.
So what we're familiar with before now are things like protons and neutrons. These are examples of things called baryons, which are made up of 3 quarks. So in the case of the proton is made up of 2 ups and a down quark, and the neutron is made up of 2 downs and an up. They don't just have to be ups and downs, they can be charmed, strange, top and bottom quarks, and this gives the sort of heavier cousins to the protons and the neutrons. There's also familiar things called mesons, which are made of 2 quarks, where you have a quark and an anti-quark pair. That is the sort of the familiar stuff.
These are the familiar stuff, 3 quarks.
But you can, and this being theorized for over 50 years now, that you can have bigger objects. And what they discovered at the LHC is finally they found an object which was made of 5 quarks, pentaquark. There have been evidence in the past for tetraquarks as well. This is all ongoing. But yeah, we now have a 5 quark guy. The one that they found is built out of 2 ups, a down, a charm, and an anti-charm. So it's a charm. That's what it's called. It's a completely new type of matter.
It's new type of matter.
So, I mean, one thing we don't know, and obviously as they do more and more experiments at the LHC, and they'll try to establish, we don't really quite know how these quarks are binding together inside the pentaquark. That's something that they'll try to learn, by a completely new state of 5 quarks. This is relevant to what is going on in the early universe, the states of matter that you might find in the early universe, and also the states of matter that you might find inside neutron stars. So now that, so when we think about very, very dense objects like neutron stars, where the neutrons are all packed together, it becomes therefore possible. You start to wonder what other states of matter can form inside that neutron star. And now that we're seeing pentaquarks form, we now have this real possibility you can have these multiple quark states that are actually forming inside stars, and maybe you think about quarks. We talked, when we were at the LHC, we talked about how the LHC could be destroyed, right? And we talked about strangelets. Strangelets are sort of states of large number of quarks. In that case, one of the relief that we might have is that the one that's being found at the LHC is actually a charmonium pentaquark, so it's more charming. Whereas the strangelets, of course, are sort of multiple states of quarks that involve strange. I mean, they only fall apart in the conditions in which you see around you. They only decay very quickly. There are many other conditions where they're more stable.
They are stable. They don't disintegrate.
In fact, indeed, it's deep inside maybe a neutron star, the possibility is that these things
It's possible that is inside the neutron stars.
It's telling you something about how the strong force is interacting.
Okay, we talk about the new discovery, new matter. There is new matter. Now we will speak about the conclusion is that stable, strange pentaquarks with positively parity can be accommodated. There is new matter. Now we have finished, we have proved everything now. We have proved that everything is positive and negative, and atoms that is smaller and bigger, the planets. We have finished. Now, for the first time, we will make claims without proof. We will speak without proof. Our idea. First time we made the conference, I spoke every time with proofs. Now, I will speak without proofs. You know why? Because science, it haven't discovered yet, so that I show you the proof. We will make claims, okay? Claims we will make. Before we make claims, I will show you a small video to show you how the computer works. So that if I tell you this is an angel, you may tell me how it's thinking. I will show you the computer and a small idea about the computer.
Zeros and ones that the computer understands what you can. And with these...
The computer is very simple. On switch and off switch. This is the computer. Very simple.
Zeros and ones. It could translate that to make any number in the world. And I know you guys are asking, how can you make any number using just zeros and ones? Well, I promise you by the end of this tutorial, you will learn that. Now just write 1 and 9. But we don't. We have this 8 that says...
Look, the computer works 1 bit, this is 1 bit. You know bytes, you have heard bytes in the computer. Bytes, yani it's 8 bits. 8 bits. They class it to 8 parts. If you want type number, each column they make 1, 2, 4. I will explain now.
So what the heck are we supposed to do? What you have to do is look at all of your bits. 128, 64, 32, 16, 8, 4, 2, 1. And there's only one way that you can add these numbers to create the number 19. So you start with the biggest number.
Now, in the computer you won't write 19, okay? How you write 19? And the computer electronics, there is only on, off. How you write it? Now I will explain.
And that's 128. If you can use 128 and 19, put a 1. If you can't, put a 0. So can 128 go in 19? No, it can't. 0.
You can put 128 in 19? No, you put 0.
Can 64? No, still bigger. 32? No, still bigger. Can 16 go into 19? Yes, it can go in.
16, it can go inside 19. You put 1 under it, okay? To 16, you can add 8? No, you must put 0.
Once. Now, what do you have to add to 16 to get 19? Do you add 8? No. Do you add 4? No. That'll give you 20. Do you add 2? Yeah, but that'll give you 18. Do you add 1? Yep, that gives you 19 right there.
This is the computer.
So in an 8-bit system, the binary...
This is the computer. It has 8 wires, and you like this 3, 16, 2, 3, it makes 19. It likes this 3 wires, and the 19 is put on the computer. This is it. 1 byte system. This is the computer. On, off. That's it, the coding system. This is it.
Code for 19 is 0, 0, 0, 1, 0, 0, 1, 1. And the computer understands this, and it's its job to take all this code and interpret it into the number 19. So let's do another one or 2. Say you want the number 64.
Okay, now you want type 64, okay?
Let me just write it right there. Can 128 go into 64? Nope. Can 64 go into 64? Yep. And there's no need, since we already have it, we just fill in all the rest for zeros right here. Right there. So the binary...
Okay, now if you want type 64, from the 8 wires, you give electricity only this one, and 64. You put on the, that's it. And you continue the bytes. This is only on, off. And the rest is coding system.
Code in an 8-bit system. And remember, 8-bit system means there are 8 numbers. 0, 1, 0, 0, 0, 0, 0, 0. And that means 64. And as you can see, by using this, we...
Okay, I gave you a small explanation, okay?